Now, the central limit theorem is probably the most important underlying idea of statistics, and it's a little bit surprising. So you need to understand that the normal distribution describes the distribution of means from multiple samples. So if I have an underlying sample distribution, so let's say rolling a die has what's called a uniform distribution. All 6 numbers are equally likely to turn up. But if I add the sum of 5 die together and I roll those 5 die thousands and thousands of times, and I plot either the mean or the total for those 5 die, I will end up with a normal distribution. So this is an example of the central limit theorem at work. And the central limit theorem says if you sample any distribution multiple times, then the mean of those samples will be normally distributed. So in that case, it was a uniform distribution. It could be an exponential distribution, it could be Poisson, it can be skewed, it could be any shape you like. It can be multimodal, it can be any shape. But if you keep taking samples and you calculate the mean of those samples, then the mean of those means will be normally distributed. It is really fundamental to all of statistics and one of the key laws. Now, the reason why I mention it here is because that die rolling is coming from the binomial, so even if I flip coins, you would get the same sort of idea. Now, the bigger the samples, the smaller the variation will be between the means. So eventually, if I get my sample to be as big as the population, then the sample mean will become the population mean. So the difference between means becomes smaller as samples become larger. Now, how can we use all these facts together? What we can do is, to start with, is we need to put the normal distribution into a dimensionless version. So before we looked at the coefficient of variation, and you could turn that into a dimensionless proportion where it is the standard deviation divided by the mean. So it's the standard deviation as a proportion of the mean. So the larger the standard deviation and the closer it is to the mean, the worse the coefficient of variation was. Now, to standardize the normal, we want to shift the distribution so it's centered on 0, and we want to have the x-axis, instead of representing units, represent numbers of standard deviations above and below this mean of 0. So this is what I'm trying to get. Mean of 0, and then minus 2 standard deviations, minus 4 standard deviations. And most of the density of the curve is between minus 2 and plus 2 standard deviations of the mean. This is called the standardized normal, or Z distribution. Now, mathematically you do this by subtracting the mean from each one of the measurements and dividing the result by the standard deviation. Now, doesn't matter what data you get, if it's height data, weight data, height of kangaroos, height of humans, height of koalas, doesn't matter what the data is, all of it will always look the same in this normal distribution. And the area under the curve is 1. So now we can turn the areas directly into a probability. So the x-axis is the number of standard deviations away from the mean. And we know that 95% of the density of this curve, 95% of the area, lies between 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. That's the 95% rule. Now, most observations are centered around the mean, the correct value. The x-coordinate can be used as a measure of error. So if I was using this distribution in quality control, what I'm looking for is making sure that my chocolate bars or my boxes of cereal do not go more than 1.96 standard deviations below the mean weight or above the mean weight. Otherwise, that indicates that something's gone wrong. That's why you'll see on the packet side of packets, when you buy something, it says E and then the value, because they've done an estimation based on the normal distribution saying that it's between this 1.96 and minus 1.96. Anything that goes outside of that should fail the quality control. So the original way of doing this was the baker's dozen. By adding an extra roll to the 12, you made sure that you had enough weight in your bunch of rolls to avoid the penalties of the law. Now in those days, it was very important to avoid being underweight, because if you're underweight, you'd be considered a thief and might have your hand cut off, or you might have your oven broken if you were a baker. So it was much better to give more and avoid ever being penalised for selling short on your bread. Now, if I collect many unbiased samples, then the distribution of the sample means, as I said, should be normally distributed. Well, not should, it is going to be normally distributed. And the mean of those means is going to be the true population mean. And the standard deviation of the sample means is something called the standard error. So this is not the standard deviation of each of the individual samples, it's the variability between means of samples. Now this is important because this is what you're looking at when you want to reproduce science. When you get your data set, no two data sets are going to look exactly the same. There's always going to be some variation. So if you're trying to reproduce somebody else's experiment, what you want to know is, you haven't got exactly the same number, but are you within 1.96 standard errors of the mean, either above or below? Because if you are, then probably you've got the same experimental result. If you're outside this range, then that means the two experiments have not been reproducibly giving exactly the same result. So this produces the thing called a confidence interval. We don't usually go around collecting multiple samples from the same population. We just collect one. So what we have to do is then estimate from the things we've collected what the standard error is and what the mean of the population is. So what we do is we treat the mean of that sample as an estimate of the population mean, and then we create a range around this in standard errors to estimate where the population mean is going to be found. Now the standard error can be calculated from the standard deviation using a specific formula.